So far we have studied about several versions of the generalized coloring, and we consider these parameters, and we proved that last time we proved that this is actually at most maximum degree plus 1 over R and taking the Shelley. No, this is not O, this is S. And as S1 and O1 are same, both of them are collection of graphs whose components are all K2 or K1. So we know that O1 chromatic number of G, which is same as S1 chromatic number of G, is at most delta of G plus 1 over 2. But of course, with larger R, these two are not same. And what happens if we increase this number? Increase this number 1 to a higher number. Haxel and Szabo and Tardos in 2003 proved that there exists large R. If you choose R large enough, then we can actually prove a better bound. We can increase this number on the bottom to 3. You might think that this bound is, not strong, because all of this, this inequality here, if we increase R, then this number keeps get decrease and decrease. However, here, even if we take a large R, we cannot, we only get 3 here. So you might think that this might not be strong bound, but we can actually show that this is not too far from truth. Because, these people, Haxel, Szabo, Tardos, and also other group of people, Alon, Ding, Oprowski, Vertigan, all of them 2003, proved the following. For any R and delta natural number, there exists a graph G with its maximum degree and most delta with its O sub R chromatic number of G is at least delta plus 6 over 4. So, however large R you take, you cannot really improve this 3 to 4. That's not possible. So we will not prove this first theorem, but we will prove this second theorem. And this shows that this upper bound, or 2 or 3, is, not too bad upper bound, as, you cannot really improve this further to 4. So this shows that this, OR chromatic number has a different behavior than these other 3 in terms of the maximum degree, in terms of its bound related to maximum degree. So how we can prove this theorem? So in order to prove this, we have to construct a graph G. We have to construct a graph G such that however you partition the vertices, at least one partition must have a large component. So how we want to prove this is using some idea related to girth and line graph. Let's say we actually take this graph G is a line graph of some other graph, let's say G0. Then we have G0 here. Then these vertices actually corresponds to edges here. And let's say this has n vertex. And this could have n vertex m edges. Then this has m vertices. And this m is, generally quite bigger than n. If we assume that this delta, every vertex has small, almost degree delta, then this is quite bigger than n, say around delta n. And if this one part has size at least n, then that corresponds to n edges here. And this component also corresponds to incident edges here. And what do we know? If there are more than n edges, we know that there exists a cycle. So if G0, if we can additionally assume that this has large girth, meaning that every cycle has a long length, large length. So if we take a large girth graph and then we take its line graph, and then if somehow we prove that in each some of the color class has size at least n, then that corresponds to edges here, and then there are n edges, so there must be a cycle, and then that cycle must be large because it has large girth, and then that will correspond to a large component here because these edges in the cycle all are incident each other, so they must belong to in one component which is large here. For this, what we need to show is that we need to show that there exists a graph with large girth. And in the line graph, it has roughly as many edges as possible while we satisfy the upper bound. Because if G0 has more edges, that means this line graph has more vertices. So that it has more vertices, then if we partition them, it's more likely that we can find one color class which has lots of vertices here. So our first goal is to find the graph with large girth and many edges. Preferably, many edges with the bounded degree means that, if this graph is regular, then this is also regular. Delta regular, that will maximize the number of edges in the line graph. So let's first prove the following lemma. This is proved by Eredish and Sachs in 1963. For any k and g, which are natural number, with say k at least 2 and g at least 3, there exists an k regular graph with girth at least g. So this is exactly the graph that we want to use here. It has large girth and then this is regular. So let's prove this. So we can actually prove this using induction. Let's write g sub kg to denote such a graph. So if there are more than one such graph, just we let one of them as a kg. then, for G equals 3, GKG exists for all K. So G equals 3 means that we don't care about the curves at all. So we can just take any K regular graph, then that's okay. So now we want to use induction on G. So we choose minimum G such that GKG does not exist. For some K at least 2. And we fix this G. And this for fixed G, we choose minimum K such that GKG does not exist. So this is two-layered induction. We choose the smallest G, and then for that fixed G, we choose the smallest R such that this doesn't exist. And then now we want to show that K, we can actually construct this GKG from other graphs which are given by the induction hypothesis. So by the induction hypothesis, we have a graph GR-1G exists, and let n be the number of vertices in such graph. So we have R-1 regular graph which has curves at least G. And again by induction hypothesis, we also know that a graph Gn G-1, sorry, not R, this is K. So by induction hypothesis, so G is smaller, so we lower the G, so we may increase the first parameter. We assume that for G-1, anything can come on the first parameter, so we can even put n. This graph exists. So what we do? We have this G and G-1. It is n regular graph. Then what we do is we split each vertex of G and G-1 into n vertices of degree 1. So what we do is we replace this into 3 vertices, and we replace this into 3 vertices. We replace this into vertices this way. So everything is a matching. And what we do is we want to put this graph in here, in each of here. And identify these n vertices with the vertices of a copy of G R-1G. So we put this. So this is the graph. And this is the new graph that we obtain. Let's say the resulting graph G prime is R regular, because again I'm writing R, sorry, KK. These are K regular, because this is K-1 regular, and each vertex here is incident with k minus 1 red edges and 1 black edge. So this is k regular. And we claim that G prime has calls at least G. So let C be a cycle with cycle in G prime. Then it is clear that C does not lie in a copy of Gk minus 1G. In each of these copy, if C entirely lies within each of these copy, then this copy itself has calls G. So calls L least G. So then the cycle has length L least G. So let's say that's not the case. Assume that's not the case. Then what we do is we contract. By the way, sorry, let's add one more thing. Such connected graph. Because any k-regular graph with curves at least G, every component of this is also k-regular graph with curves G. So we can assume that this is a connected graph. So what we do is we contract as they are connected. Each copy of G k minus 1G. Then what do we get? We obtain G and G minus 1, this. And the cycle C now corresponds to our circuit C prime in G and G minus 1. So if, say, you had a cycle looking in this way, then once we contract this and this and this, then you get a new cycle here, which may be shorter. So here this has like 3 vertices, but it shrinks it to 1. So you get some circuit. And if, say, you have some situation that you come here and then go and then come and then go somewhere else. Then this part could be, shrinked into say this. So you go here and then come back and then go. So it's, the result is a circuit. No, actually this picture cannot happen because, because between these two there are exactly one edge by our construction. There are no two edges. And between these two, we have only one, we have only one, we have only one, we have only one. So our cycle could be actually in this way. This is possible. In that case, you get the circuit, which comes here and then come back here. So this is one vertex. Anyway, so what we have is actually a circuit. Let's say this is C prime. Then, by the construction of G prime, the cycle C always contains at least one edge of a copy of GK K minus 1G. Because what was our here? So if we use this edge inside of the circuit, if you use this, because the edges in the large graph, G and G minus 1 is collection of matchings here, you must use one of the red edges to keep going. So the cycle C must contain at least one edge in a copy of this smaller graph. So we have this circuit is smaller than the size of C. But what do we know? A circuit in the graph wait, give me a moment. I'm suddenly confused about some terminology. Is circuit the sequence of edges which are not repeated, right? All of a sudden, yeah, I'm suddenly confused. Did I use the right word? Yes, closed trail is a circuit. Sorry. All of a sudden, yeah, anyway. So we have this circuit C prime, and then in this C prime, we know that these edges which belong to the large graph are now in here to form C prime. And then those edges are not repeated. So every circuit contains a cycle. So the large graph itself has a girth G minus 1. So this circuit C, which contains a cycle, also has size at least G minus 1. And what do we know? And this C prime has, because one edge contains to a smaller graph. So in this contraction, we lose at least one edge. So we have this inequality. So this shows that the cycle C has at least, length G. So this contradicts the minimality of G and K. So this proves the lemma. So with this lemma on our hand, now we can prove the theorem. So we fix any, some large integer r. And for fixed r, we want to use induction on, say, delta. Choose minimum delta so minimum counter example delta. Then, I guess this induction is not really necessary, but it's just we want to assume delta is odd. No, delta is even. Let's not use induction. Okay, I will rewrite this part in the lecture note. So if we know this holds for even delta, then for delta plus 1, what do we know? We use the same graph as delta. So assume we already know this holds for even delta. And then for delta plus 1, we just use the same graph as delta. Then that graph G has maximum degree at most delta, so at most delta plus 1, so it's okay. And if we know that this is at least delta plus 6 over 4, then because this is even number, these two numbers are same. So we automatically know for R delta. So this ensures that we may assume delta is even. So now we want to show, let's say, T is delta plus 6 over 4 and take the floor. Now we want to construct a graph which has maximum degree at most delta. To prove this, maximum degree at most delta, and then the OR chromatic number is at least delta plus 6 over 4. Sorry, here it's OR. So by the previous lemma, there exists an delta over 2 plus 1 regular graph G0 with curl strictly bigger than R plus 1. And let n be the number of vertices in this G0. And let G be the line graph of G0. So all the edges here in G become vertex here. And then two edges which are incident now become adjacent in this line graph. Then what do we know? On edge here, and then let's say this curve is bigger than 3. Edge here is incident with delta minus 1 edges, so degree minus 1 edges. Here, and degree minus 1 edges here. So if this is regular, this is d regular, then this becomes 2d minus 2 regular. So from here, you can see that G is delta regular on how many vertices does it have? Delta plus 2 over 4 n vertices. Because if this is d-regular, then it has dn over 2 edges. That becomes vertices here, so this many vertices. And we claim that its O sub r chromatic number of G is at least T, this number. So, if not, then what happened? Consider, say, T minus 1 coloring. Let's just consider T minus 1 coloring. We don't have to assume it's not. And we show that in this coloring, there exists a color class X such that size of X is at least the number of vertices over T minus 1, which is same as delta plus 2n over 4T minus 4 because of this. But what do we know? T is this number. So if you just put it here, then you show that this is at least n. Hence, X, which is a vertex set in this line graph, which corresponds to edge set in G0. This corresponds to a set of n edges in G0. So it contains a cycle, say C. By the Gauss condition, C has more than r plus 1 edges. And those edges, because they are all incident, they are all connected. Again, correspond to a component in G, bracket X, which has size bigger than r plus 1. So this shows that any T minus 1 coloring, it is not O sub R coloring because at least one color class contains a large component. So we get this inequality, and that proves the theorem. So we just prove this lower bound. And this shows that this upper bound, or this upper bound, is not too bad, in fact.